This is a video for hypothesis test for one proportion. In this problem, it's claimed that 40% of kittens are orange tabbies. Suppose that I think the actual value is less than 40%, and I do a sample, and I get 45 successes out of 120 trials. The model that I use for this one proportion hypothesis test is p hat is normally distributed with a center or an average of p, whatever that is from the null hypothesis, and a standard deviation of square root of pq over n, where p is my success rate, q is my failure rate, and n is the number of samples. All hypothesis tests follow the same 4 steps. First step is state the hypotheses. Second step is determine the model. Third step is to find the p-value. This is where you're going to compare the sample data to your claim. And the fourth step is the conclusion. Hypotheses for one proportion is always going to be h sub o, the null hypothesis, is p equals and some number. In this case, the number that's being claimed is 40%. This tells me that every time I see the symbol p show up, like I have in this model above, I'm going to be plugging in 0.40 for that number. The alternative hypothesis is also going to have p and whatever the claim number is, and it's either going to be less, greater, or not equal to that value. In this case, we think it is less, so I'm choosing the less option. This determines which way to shade. So if it's less, this will end up being shaded to the left. If it's greater, I'm going to shade my curve to the right. And if it's not equal, this will end up being a two-tailed test. My model is p hat. This tells me what to expect for p hat. So this is kind of a what-if model. In particular, I'm assuming what if that null hypothesis is true? Well, if that's the case, then I should see success rates of about 40% from my sample. It could be higher or lower, and the amount that I'm expecting that to deviate is this 40% success rate. Q is my failure rate, so 60% failure rate. And I'm wondering how samples of 120, that's my sample size, are going to vary. I'm going to type this into my calculator and see what I get from my standard deviation. And then I'm just going to draw a rough curve for sort of what we're dealing with here. This gives me 0.044 or so. So in this next step, I'm calculating the p-value. So I'm going to draw my model. Normal model looks kind of like a bell. In fact, sometimes it's called the bell curve. The center of my model is about 40%. And my standard deviation happens about halfway on the downswing. It happens at the inflection point. I'm adding and subtracting 4.4%. So that would be 44.4. And this would be something like 35.6% in that direction. Okay, so in the center of my model, I have my claim, and I'm wondering where on this curve does my data live? So the p-value is the likelihood of your sample success rate, or more extreme if the null hypothesis is true. My sample success rate for this problem was 45 out of 120. I'm going to type that into a calculator just to see what I get for my sample success rate so I can put that down on the curve. 45 divided by 120 is 37.5%. So on my curve, 37.5 happens somewhere about here. Now I need to know if I'm shading this thing to the left or to the right, and that's what the null and alternative hypothesis tell me. The null tells me that I'm plugging 40 in for the center. I did that. The alternative says I'm looking at less, so when it comes time to shade this curve, I'm going to be looking at less. So when I'm trying to figure out this symbol, this is the symbol from the alternative hypothesis. Now I have a lot of different ways of doing problems like this. but a lot of them come down to finding the z-score and then looking that z-score up. So I'm going to take my value that I care about. So I'm always going to be taking my sample minus value minus the center over standard deviation. My center is my claim of 40%. So I'm off from 2.5% from what I was anticipating. That could be a lot or a little, and that really depends on that standard deviation to determine if that's a lot or a little. When I type this into a calculator, I end up getting something like negative 0.57 or so. And looking at my curve, this seems pretty reasonable. The negative tells me that my data is less than the mound. This 0.57 tells me I'm a little bit more than half a tick mark down, but I'm not even a full tick mark down yet. So I am 0.57 standard deviations below the average. I can look this thing up in a table, or I can use technology. If I'm looking this thing up in a table, I would notice that the first two digits is negative 0.5, so I'd go to the negative 0.5 row, and then I'd find the 7 column and where those things meet up. I can also use a graphing calculator, so I could go into second vars on a TI-84, for example. I'm going to normal CDF. I'm shaded from negative infinity to negative 0.57, and this will give me the size of that left tail. In this case, I end up with a table value of 28.43 or so, and I would get about the same thing if I'm using TI-83 and 84 and 89 or GeoGebra to give me a really comparable value. If this thing was shaded to the right, I would want to do 1 minus this number. If this was a two-tail test, I would want to do times 2 for that table value. But this is shaded to the left, so this gives me a p-value of 0.2843 or so. Conclusion. If my p-value is low, smaller than an alpha level of, say, 5%, then I would reject the null hypothesis in favor of the alternative. If my p-value is larger or equal to my alpha, then I would fail to reject the null hypothesis, and I would not have evidence of the alternative. In this case, I have a large p-value. It's bigger than my 5% cutoff. And since it's a large p-value, I'm going to fail to reject the null hypothesis that 40% of cats are kittens, or orange tabbies. And this means I don't have evidence of the alternative, so I do not have evidence that less than 40% of kittens are orange tabbies. Again, that 4-step process for you. Hypotheses, model, p-value. P-value is where I compare my sample and my claim. So I have sample minus claim divided by whatever the standard deviation is. This gives you a z-score, and then you look that z-score up on a table or using technology, whatever you have available. You come up with your p-value. If your p-value is low, the null must go. If your p-value is high, you will fail to reject the null hypothesis. In this specific problem, we ended up with a high p-value, so we failed to reject that null hypothesis, which means I did not have evidence of the alternative. Just as a note, if this thing was shaded to the right, again, I would do 1 minus this table value to get my p-value. If it was a two-tailed test, I would want to take that size of that left tail and multiply it by 2 to get both of the tails.